Khoo Chee Min, and then of course to all the audience, mostly geologists. Maybe there might be some engineers. I'm not sure. I have to check the list. And let me introduce Engineer Khoo first. Engineer Khoo Chee Min, he graduated with a bachelor degree in civil engineering from UTM, University Technology Malaysia. And he also had a master's from University Technology Petronas. He's actually currently doing his PhD research under University Technology Petronas. Engineer Khoo has more than 20 years of experience in geotechnical and especially tunneling works. So he was and he still is involved in the tunnels, MRT tunnels, what we call MRT 1, 2, and 3. There are three lines. So he was also involved in some of the tunnels in Singapore as well. His current post is the Assistant General Manager with MRT Corporation. He's a professional engineer and also a fellow of IEM. So he's a very, very experienced engineer. He was also involved with some of the conferences organized by the International Tunneling Association, ITA. Of course, he was also very active in IEM, especially under the Tunneling Technical Division. In IEM, there are two divisions that the engineering geologists would be involved in. One is the Tunneling Division, and the other division, of course, is the Geotechnical Engineering Technical Division. And these two divisions are very active. They organize talks, seminars, short courses all the time. So for those of you who are interested in taking part in activities in IEM, maybe you can sign up, be a member. As a geologist, you can be an affiliate member or an associate member of IEM. If you are a member, then you are entitled to take part in all their activities. And one more thing is he has also published a few papers, more than 30 technical papers. And one of the papers, as a co-author, they won a very prestigious prize. As I mentioned before, IEM awards prizes practically every year for the best technical paper, for the best engineering project, etc. So IEM is a very, very active organization, much bigger than our GSM or IGM. Partly because they have been around for many years, much longer. And of course, there are many more engineers compared to geologists. Okay, with that brief introduction, I now invite Engineer Khoo to make his presentation. Engineer Khoo, the floor is yours.
Okay, thank you, Professor Tan, for kind introductions as well as promoting for IEM. Good afternoon to all of you, all the audience. Right, I'm Chee Min from Planning and Design Department of MRT Corporations. So I would like to take this opportunity to thank the Geological Society of Malaysia, as well as the Department of Geology, University of Malaysia, for your kind invitations. The topic of today's technical talk is geotechnical challenges in geologically complex urban underground constructions. So I hope this will be an interesting topic for all the participants here. I try to strike a balance between geologists and engineers, particularly geotechnical engineering. Sorry, I control the slide. Apparently the slide is not moving. Okay, you see the second slide?
Yeah.
All right.
Yeah, okay now.
Right,
okay.
I will discuss this topic based on the two case history in this Klang Valley Mass Rapid Transit project, which is one of the mega infrastructure project in Malaysia completed recently. The Line 1 Kajang Line, or formerly known as Sungai Buloh Kajang Line, with a total length of 46 km long, 29 stations, and operated in full line operations in July 2017, which was 6 years ago. And then the Line 2 Putrajaya Line, or formerly known as the Sungai Buloh Sedang Putrajaya line with a total length of 57.7 kilometers long, 36 stations, inclusive of 5 provisional stations, and of which 9 are underground stations. So open in 2 phases. Phase 1 was in 16 June last year, and full light openings just March, a few months, I think about 7 to 8 months ago. I hope you enjoy this metro line. So geologically, we can see that line 1, the alignment basically running through 2 distinct geological units, which are Caney Hill formations and KL limestone. The interface between these 2 formations we encounter after the Bukit Bintang station, somewhere near to the Pavilion KL. And for the line 2 Putrajaya line, basically the line running through all the 4 major geological units in Kuala Lumpur, including the Hortonen Suisse. They are a stretch of elevated viaduct, where the foundations is encountering the Hortonen Suisse. And for the underground alignment, it starts at the depot here, start with the KL limestone. Then the first underground station, KL Central West Station, is actually at the interface between granitic formations and limestone. Then the tunnel run into a granitic formations, and arriving at Titi Wangsa again is also at the interface between Caney Hill and granitic formations. Then Hospital Kuala Lumpur is actually in the Caney Hill formations. We did encounter the quartz materials during tunnelings around these areas. Then move into the KL limestone and arriving at the Kampong Baru, or currently known as the Raja Uda stations. This is located at the alluvium overlying Kuala Lumpur limestone. Going further, Ampang Park is obviously a Caney Hill formations. KLCC is also located in Caney Hill formations, and the geology changed again to KL limestone when arriving at the Collet stations. Kayak stations, limestone, Salin, also limestone, and the alignment going further south, interface again between limestone and Caney Hill at the Bandar Malaysia North stations. And then we're encountering Caney Hill, and Bandar Malaysia South station is actually Caney Hill. But of course, at the deeper depths, we encounter some granitic bedrock over the stations. Right. So as the topic of today is urban underground constructions, I would like to share with you these are the typical underground structures in metro line. So we have these 2 to 3 story underground stations, typically measuring for 22 meter wide and about 150 to 200 meter long. Some of the stations quite long, like this case, nearly to 249 meters. For the station located in Caney Hill or granitic formations, normally we adopt a diaphragm wall using a top-down construction methods. And for the station located in the KL limestone, like this case where the limestone height is reasonably deep, so we'll have this sequence board power wall as the earth retaining structures, plus together with the temporary ground anchor as a tie back. So for this case, quite a deep station, 4 to 5 story, but the rock head is quite shallow. So we adopted just a ground treatment gravity wall as earth retaining structures. Both of these is constructed using a bottom-up method, so it's actually open cut into a limestone formations. So for this case, it's another 5-story stations where you can see the alignments actually in configurations, one upper, one lower, and located in the Caney Hill formations using diaphragm wall top-down constructions. Other than these underground stations, we have the ancillary structures along the alignments, such as interventions and ventilation shaft, we call it IVS, or maybe escape shaft. So when the shafts are located within the alignment, we call it online shaft. And when the shaft is located at a distance away from the tunnels, we call it offline shaft. This is mainly because of the surface congestions where we can locate the shaft right within the alignments. So like in this case, there are one offline tunnel and one tunnel is within the shaft. For this shaft, normally are constructed in the circular shapes. Of course, in a certain instance, they are rectangular shapes, and normally they are deep. So we adopted a bottom-up construction methods. In terms of the excavation depth, the underground structure mainly are, I would say, 20-meter deep or deeper than that. For Kajang line, the deepest stations is actually the TIX stations located in limestone formations, 44.5-meter deep. So for others, 4 stations located in new formations where we adopt a diaphragm wall, the diaphragm wall thickness is up to 1.2 meters and quite reasonable tips up to 50 meters. So when we built line 2, started in 2016, the station is actually go much deeper than line 1. One of the reasons because of the complexity of the underground spatial developments in Kuala Lumpur. Like for example, some of the tunnel have to undercrossing the existing underground infrastructures like smart tunnels. Even the line 2 tunnel have to undercrossing existing line 1 tunnel, for instance, near to the TIX, where these 2 lines actually interchange. So because of that, you can see the stations have to go deeper. And for line 2, the deepest excavations is IVS 2, 57.5 meters deep. I believe this is the deepest excavations that we as an engineer face so far in the KL regions. So we can see that even for diaphragm wall also go deeper and deeper. And the size is even up to 1.5 meter thick for Ampang Park stations. And even KLCC station also 1.5 meter thick. So all these are the new challenges that the engineers and the geologists have to face in these projects. And now, these are the underground stations superimposed into Kuala Lumpur maps. You can see they are mainly located in the congested urban built-up setting areas. Some other stations are actually located adjacent to the tall tower, high-rise buildings, all these. Some are even located near to the important building structures like national museums. Merdeka station is actually located just right beside the national stadiums. And of course, the currently 118 Super Tall Tower. Same thing for Tun Razak, also located right next to the Super Tall Tower, 106-story height. Of course, if we are lucky, sometimes the station will be located in a reasonably greenfield conditions, but it's not totally greenfield because we are working in the Kuala Lumpur areas. It's actually a brownfield. Some of the existing building has been demolished and it will be developed later. So like in this case, the Cochrane station, this photo is taken in year 2012, where you can see the Mai Tao, the IKEA has not been developed yet. So another case in point, even in line 2, this is the Bandar Malaysia North Stations. As you are aware, is located in the Sungai Besi airfield. I would say it's reasonably okay, but of course there are another set of the challenges like actually Bandar Malaysia South actually located right next beside to the heritage control tower. So it's also quite a difficult construction site. So of course, when going into the KLCT areas, the stations actually can, like in this case, Bukit Bintang station, just located underneath the major busy Giant Bukit Bintang. So you can see the station construction actually is carried out in 2 phases. One is next to the McDonald's. It's right beside the building, just about 4 or 5 meters away. So they have to close the traffic and divert traffic to one side, start to install a diaphragm wall. Then once this is completed, then move to another site beside the Selangor, Selangor buildings. Then start to do excavations and proceed downward with the top-down constructions. Of course, now you may not aware that because the construction has been completed, we are just enjoying the underground station beneath this busy area. Right. Next example in line 2, like these Conley stations. The station is actually located just squeezed between the existing tower, between the buildings. Of course, at the area where we can do this station, by the way, is about 30 meter deep, located in limestone formations. Where the excavations we can proceed with the open cut with the SPP ground angle, we do that. But at certain locations, you can see, like in this case, we cannot install ground angle anymore because there's existing building, existing basement, so we have to opt for temporary strutting conditions. This is quite interesting combinations of ground angle struttings all the way. By the way, this is also located near to the, if not mistaken, it's Istana Hotel, a well-known hotel, right? So other than underground stations, we also need to build the tunnels. Just some information here. Somebody asked about the tunneling. So for line 1 tunnels, 9.5 meter long is a twin tunnels. Geologically, about 45% in limestone and 55% in Kenny Hill. It's quite distinct between these two. When we come to line 2, as I say, all the geology we have to face, not even in the underground station excavation, but in the tunneling as well. Limestone, 39%. Kenny Hill, just still majority, 44%. Granite, 14%. And the other challenges is this mixed formations where the tunnel is actually driving through the alluviums, or maybe a fixed phase condition between soil rocks is constitute to about 3% of the total alignments. These are just a pictorial representations of the tunneling in the various geological conditions. You are well aware about the nature of each geological formation here. All right, and for today's presentations, I will talk about the 2 project sites in Putrajaya line. Both are the project site located actually is limestone formations, KL limestone, but it's just I would say extremes of the both spectrums. So the first project site or construction site is actually this hospital KL crossover, 20 meter deep excavations, but the limestone formations varies, the limestone rock heads actually varies from 18 meter below ground to as deep as even 100 meter below ground. And we face a lot of issue in this construction site. So the second site is another extremes. Not only the limestone is deep, in KL region, we sometimes face the limestone is very shallow. Just like in this case, the Chan Sao stations, the limestone rock head can be quite near to the surface. So just about 4 or 5 meter excavations, you will encounter the limestone bedrock. But for this case, we encounter a very deep limestone trough running across the stations. These stations are 40 meter over deep. The limestone trough can be as deep as 30 over meters. But between these two, I will talk in more detail about this hospital KL site and briefly walk through the second site for the shallow limestone, and depends on the time permits. So I might run very fast for the second site. So for this hospital KL, I will start with the unforeseen surprises. It is really a surprises to us as a geotechnical engineer, I believe also for geologists as well. Then I will talk about the geological and hydrogeological models. What are the associated geological risks, and how we actually prevent or actually we mitigated that problem, the geological problem, the risk. Then I will follow with some performance of the constructions with the monitoring records, and I'll wrap it up with some lesson learned. So let us start on the first construction site, though. Hospital KL crossover. I just name it as a HKLX. Location-wise, is located. I believe you are familiar with the KL context. It's located next beside the IJN, Institute Jantung Negara, beside Jantung Razak and bounded by this Jalan Raja Muda Abdul Aziz. To the south is actually Kampung Baru. So to the north, there are some landmarks like Istana Budaya, National Art Gallery, Pusat Dara Negara, as well as the National Library along the Jantung Razak. So actually this underground structures is located between the hospital KL stations and Raja Uda stations. The other point to note is actually also quite near to the Sungai Bunus, is running through at the boundary of the site. So for your information, why it's called crossover box and creeper siding track, you can look at the layout, the two line, the red line and the blue line, which denotes the two tunnel or maybe the alignments. Red is the southbound, blue is the northbound. So at these underground facilities where the line or the train actually can cross from one line to another, you can see the red line. If needed, it can cross over to the blue line, and blue line can cross over to the red line. Of course, to the side of it, you can see there are another two straight lines, where, as we call it, a creeper siding track, where for those creeper train, where the train have a problem, whatever, they can stabling, or maybe in the layman term, they can park in this creeper siding tracks while it will be pulled to the depot for further maintenance. So these are basically the context of the HKLX. It's not a station, you can't access here, but it's meant for the railway operations and maintenance requirements. So more important now, I would like to draw attention to the adjacent existing building structures. First of all, so for your information, for the purpose of these presentations, I will follow, call it to the right is western part or western sections of the HKLX, and to the east, to the right is eastern part. Instead of the true north, they will be quite confusing. But just for simplicity, I will just follow western on your left, eastern on your right. So Hostel Sejahtera, Hostel Harmony, and Hostel Abadi are actually the quarter for the hospital staff. It's located in the south in this case. Then to the north, there are some existing building structures like hospital ready care office. It's actually a low rise, I think about 2-story. There is also one PMB substation, quite major one. If I'm mistaken, is a PMU located to the north, quite near to the box structures. And then of course, Sungai Bunus is actually now in this eastern side of it. So the box is about 31 meter wide, long 230 meter long. So the depth, as I mentioned, 20 meter deep. So it's not a simple underground structure, just 20 meter deep compared to other come up to 40 meters. But this is relatively shallow in a way that 20 meter, wide 30 meter. So the temporary earth retaining structure system adopted in the design are temporary struttings. There are 4 layers of temporary strutting strut across the diaphragm wall. The diaphragm wall is also 40 meters. 40 meter deep, so it's not very deep. So in this case, you can see the depth of excavation is 20 meter, then the wall embankment is another 20 meters, one time the excavation depth 40 meters, and the embankment is actually strengthened by this cross wall. Actually, it's also one type of diaphragm wall, but it's built across in a transverse directions across the box structures at a 50 meter interval. So we call it as a cross wall. Then to the right is the permanent conditions, permanent box conditions. Of course, as usual, we start with a desktop study. We look at the geology maps and let's see what do these geological maps tell us about. So in the version of 1976, the location of this site is located in the KL limestone, quite near to the quartz dikes, right? You can see the revolve maneuvering there. Then in the version of 1993, also in the Kuala Lumpur limestone, but in this version of the map, the quartz dike is actually moving further north, right? And 2011 version is quite similar to 1976, although the legend used is a brick format, but it's also confirmed in KL limestone formations. So it's no doubt that all these versions of geological maps suggesting that the site is actually underlying by the Kuala Lumpur limestone formations. We even trace back to this quite old documentations shared by one of the engineers. Sorry, I don't have the source of these maps, but it's called Geological Sketch Map of Kuala Lumpur. I think it's hand sketch. So again, I believe these versions of informations was developed before independence, maybe early 1930 or 1940. Maybe I think Prof. Tan or maybe some of the geologists here can advise. So it's confirmed again, the site is Kuala Lumpur limestone, and there are some indication of bending strikes, right? So there is a reason why we trace back to all these site history informations. I will deal with it a bit detailed later. So as I mentioned just now, construction started in 2016, and 2015 we actually were in the reference design stage. There are 4 borehole plans, and eventually when they issue the tender document, only 2 borehole completed, which is indicated in the red borehole here. And the other blue borehole here is actually about 100 meters away from the box structure, if not mistaken. These 2 has been completed at that time and issued for tender information. So from here, the engineer classified the overburdens in terms of pre-nominally granular materials for those sand, gravels, and pre-nominally cohesive material for clay and steel, which is in the brown color, and light yellow or this color is granular material. So no bedrock was encountered from these 2 boreholes. And for the engineers, you can see the SPT is generally range from for the red boreholes actually 0 to 20 pounds, and for the blue boreholes it may be extended further to more than 30. Occasionally there are 50 and localized areas. So the maximum depth of these investigations is just a 50 meter below ground. So, and followed by this another 2 borehole completed sometime in October. Sorry, for the first RD12 completed in 59.4 meter, and now we encounter limestone at a depth of about 50 meter below ground. The SPT wise almost similar to the earlier red boreholes. Then another borehole RD11 follows suit, also completed in October. For this borehole, we drill as deep as to 71 meter. No bedrock was encountered, and this borehole was terminated because it fulfilled the termination criteria in terms of the hard materials, where we define as a SPT value more than 50. So you can see the profiling here. 0 to 20, SPT at about 6 to 10, 20 to 40, it increased with depth 12 to 38, and 30 to 55 meter reaching 50, and 55 to 70 meter for another 15 meter thick is actually high material with an SPT value more than 50. And there are the unforeseen surprises occur. The first incident was this large ground depressions. It will occur when the contractor is doing the borehole. For this is a new borehole other than the 4 numbers of borehole. carried out by the bidder during the standard stage. This is a very deep borehole, if not mistaken, down to 100 meters deep. But when the borehole is completed, when the contractor withdrawing or obstructing the drill lots, it caused a ground depressions at the car park areas. So the borehole location is actually here, but it's quite a far-reaching kind of the impact. So it's here, typically we say diameter wide could be up to about over 20 to 30 meters. And at a certain area where the ground is weak, actually the ground is distressed with all these cracks. This is a depression. So this photo is taken about 6 days after the incident was reported. It's very strange. How can business during a borehole of 4-inch in a KL limestone area, it caused such a ground depressions? It's not sinkhole by itself, I would say, but just a depressions down. And going forward, the contract was awarded in first half of the 2016. Then the successful contractor proceeded to do their own further investigations. You can see the blue color are those borehole completed pre-awards, meaning either by the employer side under reference design, or maybe by the bidder during the tender stage. Then post-award, the contractor carry out those additional borehole along the station parameters, typically about 50 meters apart according to the contract requirements. So let us see what happened next. Awarded in March 2016, then the contractor carry out their borehole and carry out the detailed design in sometime second half of 2016. So when contractor go to the ground to carry out their grouting, because it's made aware that this site is quite very problematic. So in the contractor design, they require these ground treatments using a compaction grouting. When they start to do in early 2017, there was another second incident occurred. So you can see in the layout here, the site is actually the epicenter of the ground depressions. At the point of time, let us see what are the activity on site. So please remember, this red borehole are the first incident occurs where the borehole named as, just put it simply, PB3AR. This is the locations where the drill, the first borehole drill caused depressions around these regions, the covered regions. Then when on this day itself, the contractor, when doing the grouting point, it occurred a second incident from here. At the time, this reading is down to 93.5 meters. There are two locations where the contractor is doing the SI 9 meters over here, and this area about 38 meters. Another machine is used to do the rock popping along the wall. At that time, it's 29 meter tips. So these are just some of the photography record. You can see when the incident was reported on 4th January, around 4:45 p.m., the ground depressed. Look at this, genset is actually tilted toward that. Then the second photo at 7 p.m. on the same day, the ground is depressed or settled further. So of course, the genset have been moved away from the locations. At the night of the same, at the night of the same day, and the second day morning, 5th January, you can see even the ground start to crack. It formed a circular shapes around the epicenters. So here are another photo showing the afternoon of the second days. You can see it's actually a cone shaped kind of the ground depressions, crackings, and the second day the contractor installed the building settlements, the ground settlement markers to measure the development of these ground depressions and ensure the ground has been stabilized before we move on with the next course of actions. These are the 5th January. In the mornings, it settled quite substantially, and we can see the afternoon it start to stabilize. So this is just a representation of the extent of the depressions. The first record estimated diameter 50 meter wide, depth 0.5. Then it developed further to 22 meter wide. Depth also increased to about 1 meter deep. And the ground is propagating outwards, right? At the morning, at the night times of the incident days is extended up to 25 meter diameter wide and about 1.5 meter deep. So the second day, the ground is still propagating, but in a slower pace. So, and as estimated the volume of ground loss or the ground depressions is about 300 meter cube. So we can see that this kind of incident is not like usually we see a sinkhole, very suddenly created a hole, but rather that is progressively the ground depressed downwards and forming a cone shape. So it's very surprised. It's very unforeseen and unusual, I believe, for most of us. Then, because of all these issues, the employer decided to commission an independent expert review, trying to understand what actually happens here. It's just a limestone formation, it's what we have seen before, but this is an exceptional case. And because of that, so there are more thorough investigations or maybe a desktop study traced back to the historical map up to about 120 years ago for this 1908. The main idea is to make sure, because there are some argument arise at that point in time, whether the ground, can it heal overlying limestone, where we normally see slump zone happens, or is it over alluvial overlying limestone? Or maybe some party also claim that there is possible a mine healing, because you understand that this location is located right beside the Titiwangsa Lake and towards the Seta Park. There used to be a mining activities. So that's why this map is investigated. Of course, from here we can see there are some dots near to the sites indicating possible habitants 100 years ago. But of course, at that time, that point of times, we believe that the dredging method for mine activities is not there yet. So of course, another question also arises that because the borehole is still drilled down to the 100-meter deeps and encounter limestone relatively deep. So the questions arise whether it was a mining before and then backfill for such a deep locations. Because looks like it's quite unlikely to and 1935. So we can see there is a quarantine. We believe it's a hospital quarantine area, some building near to these locations. Same thing for the maps in 1935, pretty much the same. Of course, in the map 1922, we can see the mining activities towards the Titiwangsa areas. Same thing for 1935, to the north. So another map is 1945. It's pretty much similar to the earlier 1920s and 1930s. Not much of a change over here. And this is the aerial photograph 1955. So when you zoom into it, almost quite similar. There are some buildings, hospital buildings there. Then mining activities are mostly to the north of the site. And we have this 1974 National Mapping Malaysia showing all the mining activities. Again, it's pretty much similar. Of course, the area is further developed with the buildings, roads, right? then Kampong Baru to the south. Sungai Bunus is pretty much there. Then this map is 1995 so-called geotechnical maps made available to us for study. The dots are those mining activities. Well, it comes close to the site, but it's not exactly at the site also, so to speak. So this geological map also shows the quartz dikes to the north, right? Okay, pretty much similar. Then what about the recent back aerial photograph? We can see here in year 2004. These four buildings are actually the Hotel Sejahtera and the Hotel Harmony, not mistaken. Then the site location, actually there are low-rise buildings, I believe is the quarters for the hospitals, and these are the Ready K office is still existing there. 2008, almost similar. 2010, then the low-rise building has been demolished. 2011, they make the site into a open car park lot. 2014 the same, and 2016 where the contractors actually take over the site for the construction. You can see the earthwork started here. So these are pretty much of the site history study and the look at the study on the mining activities. And this layout shows the borehole completed by the contractors. Those three boreholes highlighted in red, I'd like to draw your attention because slime zones were encountered in basically these three areas. Number one, the first incident occurs with this is a PB3AR. Then when during for this borehole PB3, also limestone encounter, and to the west, sorry, to the east, in this case, another borehole encounter limestone and CBR 85. So with borehole label with L's, actually the limestone rockhead encounter. Some are the borehole terminated without encountering any limestone. Let's look at the geological profile. I hope you can see it clearly. For this presentations, the engineer actually put it in terms of the predominantly silty and clay, like previously cohesive materials, predominantly sandy and granular materials. You can see here even a Kenny Hill with a question mark. Is that a Kenny Hill there? And this is the weathered or hydrothermally altered granite. I think it's quite interesting geological terms. And of course, these another two legends in limestone, mostly less than 50% recovery, and this legend is more than 50% recovery. As I said just now, there are three areas where the limestones encounter. Number one, let's look at this group, PB3A and PB3. The depth encountering limestone is 46 meters for this borehole, 14 meters thick slime zone. When we define a slime zone, meaning that the SPT value is 0 or maybe hammer weights. So another borehole PB3A, the first incident occurred slime zone encountered at 69 meters deep below ground, thickness 27 meters thick. The second group, PB3R or PB3RA, 51 meters, thickness 25 meters. For this borehole, 69 meters, thickness 25 meters. And toward to the east, another borehole also encountering slime zone 60 meters deep, 11 meters thick. So we can get a sense that the slime zone is actually very deep, generally below 60 meters, 40 to 60 meters below ground levels, quite thick, even 10 to 20 meter thick kind of the slime materials. The photography showing the material sample from the split zone. For this is the CBH 85 to the east side. And you can see quite sandy in a way, gray materials. and this is in the middle of the box structures, PB3, at a depth of 46.5 meter hemo width, and another samples into the brownish color, also hemo width. So when you look at the SPT value, we can see the SPT is increased with depth up to about 50 meters below ground, and of course below that, where the SPT zeros encounter down to about 80 meters. So basically, the color is actually the blue are the pre-awards boreholes, and the red are post-awards. Of course, for these slab materials, they are blue color encountered in the like borehole PB3R, 3AR also. But this gives you a sense that they are very thick and very deep below the ground. So this is one of the versions of the geological profile generated, and this representing this line of the retaining wall. We call it a sub-bow. The next one will be another geological profile generated for the northbound alignments or northbound wall. You can see the profile is very erratic based on the borehole levels, and there are some cavities encounters. So the northbound alignments looks like more simple compared to the southbound, but also quite erratic. And here, we'll highlight here, you can see there's people, and actually in these geological maps, earlier they just differentiate in terms of two, either soil or rock. Rock definitely is the limestone, but for soil, you put it there, alluvium, slope, or mine tilling. So at that point of time, it's not certain yet whether the overburden material is actually a mine tilling materials or the deposited alluvial material. So there was certain argument between not argument, actually debate between the party involved. But what we can see here, we also encounter hard materials, SPT more than 50 to the western part, highlighted in the yellow zoning here. So, wow, and just statistical wise, the highest rockhead encounters to the lowest rockhead encounter range between 55 to 60 meters in this longitudinal profile. So I've cut two sections here, section AA in the middle of the box structures, and section BB to the east where the first incident borehole was encountered. Let's look at the cross sections. Look at the left side section AA. You can see actually the limestones, the slime zones. Slime zones actually in the middle of the box structures. There are two boreholes drilled at the retaining wall, but encounter limestone at a higher depth. So it's suggesting that the slime zones actually in a limestone trough. Then moving forward to section BB, also similar, but to a surprise that you can see to the right, the limestone is much higher. This is where I think it's a shallower limestone, sub-bow, 80 meters below ground. And to the left, the limestone encounter in this case is about 65 meters below ground. And the slime zone is 20 meters deep, right in between this trough. With that, I will give a bit more details in the next few slides. So how about the cavities? The cavities that are actually infill, and when during there are some core loss. So in this area, the recovery is very big, right? And of course, we also scrutinize the borehole logs and found that actually the cavity infill and the groundwater is maintained over the night. So it's suggesting that the cavity some way disconnected. So it's actually not a solution channel or maybe empty cavity where normally if you encounter that, you will have the water loss quickly. The other point of view is actually for this so-called cavity aerials, the SPT was carried out and it's revealed that the N value is actually quite high. So some of them are more than 50. This is another borehole NCBH, just now NCBH 80, now it's NCBH 81. Same, you can see the groundwater is actually full overnight in field, and this is relatively deep, 89 to 92 meters, high SPT value. So what does this tell us? Is it our interpretations correct? Or there may be something else, because we know that the karstic features is up to your interpretations. So you have to look at the three dimensionals, not only in terms of the depth where we say it's a trough, but it can be extended laterally and diagonally to other areas. So for this case, because of the point I highlighted just now, infill cavity, high SPT, and then it's disconnected. So we don't believe it is a floater or it is the rampants of the limestone materials. You can see it's relatively thick, for this case about 5-6 meters. We rule out these situations. We believe this would be a most likely situations. It's a trough, this trough in between, right, sandwiched by these limestone formations. No, previously it can be a full limestone because of this weathered and slammed into the cavities, it created a trough. Then these two areas, it might be one day become the same things. So this is an interesting part. We talk about the water loss in the borehole. For that two borehole, although it's no water loss, but of course we also encountering water loss in other borehole as highlighted here in the yellow dot over here, and mostly majority are located around this southbound alignment. You can see that the limestone also higher and more cavity encountered in the southbound alignment. Right, this is just a representations using a 3D modeling for the limestone areas. You can see quite thick and extend laterally combined between the group of the bowl 3R and the 3AR. Then to the right is actually the NCBH 85. Now, of course, this is another modeling for the limestone encounters. But I would say this is different from our interpretations because limitation of the models. That's why you have to be careful. You have to know what you are dealing with. This is just showing the limestone in layers, but what we interpreted that is actually a solid limestone with a deep trough. Right. Now we what is known for the ground conditions, the site is underlain depth by limestone, and the rock varies from 80 meters to as deep as more than 100 meters, right? And there are some cavity in the limestone, and the material, the overburden materials consists of sand, silt, clay, gravel, all the material we have, you can name it, we have here. SPT variables are more than 50 meters. Sorry, more than 50 blow count. Slime zone quite deep, 45 meters. 45 meters is actually lucky in the sand that is actually below the toe of the diaphragm wall. Remember, just now I mentioned 40-meter deep diaphragm wall. So it's also intended try to avoid disturb all these slime materials. So of course, just a note, did you know I will skip that? Great. I think it's time running. Then, of course, just how I mentioned, there were discussions whether the old-lying materials actually belong to canal formations or alluvium deposits, or even a mine tailings. So this is an interesting part where we have very thorough technical discussions, debates among the expert here. We have expert A, expert B. They are the project design consultant, and expert C in this case is actually the independent consultant commissioned by the employer. So first of all, both consultants do not think that the material can heal formations, and of course this is agreed by expert C. So they have their point at listed here. But expert A does not seem to consider the possibility of the alluvium deposit as the overlying material. So expert A thinks there is a mine tailing. Let's see what are the points put out by expert A in his view. Number one, low SPT value. Expert A claimed the materials was possibly pumped or backfilled without any compactions and further disturbed by slumping into the overlying limestone. Because the color white also suggesting that the iron oxide may have removed during the mining operations. Then the third point, the materials varies widely in grain size, poorly sorted and display no bedding, laminations, and graded beddings. The expert A point of view is kind of artificial environments of a retention pond similar to the mining. Because the fourth point here is Bollock register the material as a completely weathered candy hill formation from quartzite. So you can see the photo in the upper right. There are some muscovite encounters and even some iron oxide. So probably weathered from the sulfates, right? These are some of the case examples put out by the expert A, because they are the woody materials encountered in one of the borehole. And now let's look at what are the expert B point of view. This expert B is even interesting, try to put it into equations to the engineer's understanding. So first, let's see at the abbreviations we use. I will go a bit slowly. SZ is the slump zone, mine tailing empty, alluvium deposit AD. Then we have young alluvium YA, old alluvium OA, canal formation KH, limestone LST, and this just a general overlying material or limestone OVM, and of course N is the SPT value. The point put out by the expert D, saying that if slime material is not mine tailing, overlying material cannot be mine tailings, right? Logic not possible. Alluvium material overlying mine tailing at the slum materials. So the experts also see that the N value is relatively high. It's not a typical range that encounter for the mine tailing where slime could be 0 or maybe up to the SPT 5 or loose sand, the kind of situations. So point number 3, if the slime material is mine tailing, meaning that the trough has been cleaned out before the tailing materials being dumped back and backfilled back. But it's just two extremes. We are talking about 100 meter deep in this case. Then of course, when we study back all the historical maps, geology maps, there are no indications of the mining activity at and in the immediate vicinity, but to the north, yes. So based on this point number 2 and point number 3 above, the expert B argued that the overlying material is not mine tailing, and then slime material is not mine tailing. So perhaps the answer lies now with the alluvium materials, whether it's a young alluvium or old alluvium. So basically, young alluvium comprises of unconsolidated sediments, of course. Then old alluvium is longer geological history for formations. For old alluviums, actually, it can be dated back to 10,000 years ago. Then from young alluviums, actually from present to 10,000 years ago. So OA, it can be semi-consolidated, and because of that, because of the salvage consolidations, it can be thicker and higher SPT as compared to the young alluviums. From the other point of view is the N value for young old alluvium is actually lesser than the end value of the kidney hill. So in this case, the slime material for the old alluvium and limestone interface could be developed more faster, more readily. That's why you can see extreme thickness of the slime material encountered in this case up to 30 meters. Right. Then in the engineering significance, the expert B also put in this where the slime material with the SPT 0 is actually the weakest compared to mid-tailing, and then compared to young alluvium and the old alluvium. As of course, the kidney hill is a stable material in terms of soil strength and the stiffness. So the expert C saying that most likely is the old alluvium based on the DEX study, based on the sample inspected, based on the depth. We are talking about 100-meter deeps, and based on the variability of the rock heads and the narrow trough that we can see here. The other interesting point, he argued that also if this is a mid-tailing site, in this such a very narrow situations, you need to deep down 30 times 30 to 50 meter deep below the slime materials. It could have mean that you have to dewater for more than 50 meter deep, but this is in the center of the KL urban area, although we are talking about 50 to 60 years ago, but it's quite ridiculous in a way. Then expert C also interesting, talking about the high SPT value might not be expected unless some compaction for the minorly. Not only high SPT value, it's also mentioned not merely low SPT value in the overburden, the first 50 meter overburden, so it's unusual for mid-tailing. So of course, wood fragments can be found in the alluvium depositions as well. So it's quite interesting. Moving forward, as engineers, technically, what we see more important to us is actually the performance, the engineering performance or the soil parameters of the materials. That is more key and important for us to carry on with the geotechnical design. So the significance of whether the material is mid-tailing or alluvium is actually the more important is lateral continuations of the layering and the loose pockets observed at the high layer, whether it extended to a far area to the adjacent structures where we can bring construction's impact, that is more important to us. So when we see at this, it's not only at one-dimensional or two-dimensional, but three-dimensional is rather. Sinkhole mitigation measures. We learn from the literature, almost all the sinkholes are triggered during construction activities. Right, main triggering factors can be like lowering groundwater tables, then loss of fine wash out by this groundwater into the voids, right? Imposing additional loads or maybe vibration due to piling, punching of cavity either by borehole or pile. These are some of the factors. So bearing this in mind, the prevention strategy adopted in the design first is to ensure construction load or maybe the permanent load is less than in situ. So now you can see why just a 20-meter deep excavations, we adopted a 40-meter deep diaphragm wall, one-to-one excavations is not deeper than that, with the intention trying to avoid and try to not increasing any load to the deeper slime materials. Then preventing drawdown of groundwater pressures is important, preventing seepage flow into the limestone area, and of course prevent the flow of the fine into the underlying cavity is also important. So this, as I mentioned just now, the design principle for the permanent structures, skip this. And the third point is actually the base slab was designed as a deep rough foundations. It's not only relying on the diaphragm wall, but the base itself. And well, the fourth point is the compensation foundations without increasing any effective soil stress at depth. Then for the uplift is resisted by the diaphragm wall. So not only a normal design, so because of these complexities and all that, the engineer is actually carry out additional analysis to stress test, in this case, to stress test the permanent box structures, considering the slab material that we encounter at that 3 locations, right? So there are 3 areas, zone A, B, C. Quickly run through, basically just variations in terms of the spring stiffness. We step down the spring stiffness from 100% to 75, 50, 25%, 10% from the baseline to see how tolerable of this permanent structure design. So for this case, to the northbound, to the south, you can see that the limestone is much deeper. So the spring actually, we have decreased it to 0%. Then for zone B, the limestone materials to the NCBH 85 to the eastern, again, the same things, different in the spring stiffness. Zone C at another corner. So with all these 3 zones, is represent the entire box structure design. And what we can conclude from the analysis is actually the design is pretty much intact, even with the spring reduced to 50 or 75%, the settlement is still tolerable. So, and then how about the residual risk? Because all this is cost, so we have to balance between the cost and the risk for these areas. And we decided that to adopt these compaction groutings as a solutions to it. There are 2. One is the compaction groutings. Basically, is to identify the slump zone. It basically is a grouted columns zone, providing extra strength, stiffness, and reducing the potential of the flow. And the other is capping grouting around the interface between the weak slab materials and the rockhead. So this is the figure showing compaction grouting and the cap grouting to the right. So these are the typical termination criteria. So this is the typical compaction grouting record. You can see where the value increase blowouts is where actually the weaker or slab materials was encountered. And you may ask, how about the first ground depressions incidence areas? It shows this at these trough areas, generally higher volume intake and higher pressures is exerted through all these compaction groutings. So other than compaction grouting, of course, for the diaphragm wall, cross wall, we have a rock popping, and this is just a spatial representation of the ground intakes to the southbound alignments. The balloon is larger, indicates more volumes is required for the groutings. And in this, all the total borehole, drill hole, running rock popping holes for this project site. So you can see the ground holes is sum up to about 150 meter point with the total ground intakes more than 2,000 meter cube being consumed by these underground areas. Just a point to note here, although this controlling is generated by Surfo, but of course we do not recommend to generate contour using for the limestone bedrock. Of course, you have to be more careful because I understand that the limestone is erratic, up and down. It's not like granitic for all other bedrock formations. So you have to be careful when you generate it using Surfo or other limestone.
Excuse me, Engineer Khoo. Sorry to interrupt. I think we kind of overshot the 1 hour.
I know. Run a bit faster. Sorry.
So I think we have to wrap up pretty soon. So we leave some time for questions. Okay.
Sure.
Yeah.
Okay. So for that study, it took about 2-3 months. Then actually the real problem still happening on site after a grouting point. We can see this is a hotel situator located about 50 meters away, and one ground settlement point. See the ground is actually settled up to 60 meters mm without any major excavation, just doing the borehole grouting point, but the ground is settling. Even the building also settled more than 10 mm at that point of time. This is very unusual kind of settlements, suggesting that it could be due to consolidations, the groundwater issues. And we carry out a hydrogeological review. These are two sets of the groundwater that gather from the borehole. The blue is actually this three borehole located to the western side. Generally, the ground is higher, so the groundwater table is in terms of IL 32 meters. And for another set, lower ground level, the starting point is about IL 30 meters. But it's very strange that the water keeps dropping after the standpipe has been installed. You can see a timeline is sometime in June, August, but the water is keep dropping until the first incident occurred in November. Then since then, it begins by another meters, then come to the second incident. So this is a review of the standpipe. You can see one of the issues that we identify as probably because of this standpipe detailing, where normally just a 1 meter pipe on top, and then below that is a very thick sand pegging area. So this is actually encourage the flow of the water. What more important is actually we encounter a perch water table in this area. With the upper layer, the water level, the water pressure is actually in a hydrostatic form is up to 34 meter reduced level. But for the lower level, it gets back to about 27 meter reduced level. So actually they are a kind of aquifer at the deeper depths. And because of the sand packed in the long standpipes, actually the upper water regime flowing down to the lower, causing, it could be possible causing the ground settlements. So with that, we identify that water could be the most significant risk. And this is also a typical problem when dealing with the excavations. So these are just some sketch showing that possible the water will flow through the limestone, the porous limestone with a higher mass permeability and cause base heave or maybe a sinkhole problem outside the box. So for engineering, we only need to analyze for the seepage for the normals within diaphragm wall within the soil, but we need to analyze also for the diaphragm wall located into a limestone in light of this possibility of the problems encountered. Skip this. Then this is the seepage analysis for the diaphragm wall in the limestone. And what would you predict in this case? And moving forwards, another 6 months down the road, end of the 2017, the ground is still settling, although the rate of increments is slowing down. So at that point of time, activities, DWAL started in March, then the excavation started in June. So by that time, the grouting work has been completed. And for the building settlement, it behaved the same thing like a ground settlement at about 50 meters away. So bear in mind that this 20-story tower building is actually supported on pile, but on the pile foundation is still settling like ground, similar kind of situation. Settlement mitigation measure, of course, we shorten the DWAL.
Sorry, Engineer Khoo, I think we have to stop. Sorry,
right, no problem.
I have to stop because we have to leave some time for questions.
Okay.
Yeah. Okay, so I open to the floor for questions. Sorry, Engineer Khoo,
no problem.
We run over time.
Because it's
injury time. Injury time already. Yeah.
Yeah, I understand. Sorry about that for time control.
Yeah, it's okay.
So sometimes sure it's nothing, just continue there. Yeah.
Right. Any question from the floor? Any takers? How about Mr. Robin Liao? You are keeping quiet today. No?
Okay. Thank you, Mr. Tan.
Yeah. Yeah. start some quick questions, then we give chance to others to ask as well.
This is really intense, really intense.
Okay.
Just like last month.
Okay.
But this is really intense. We are walking through the geology of the Kuala Lumpur area.
Yeah.
Starting from the Hotterdon schist, Ordovician Silurian, KL limestone, the Carboniferous Permian Kenny Hill, and the
Yeah.
Triassic granite, the quartz dike, the alluvium, the young, the old alluvium, and then we have the what they call this mining tailing problem and the groundwater problem. This is
Okay.
really
Robin,
complicated.
quick
But
question.
yes,
Quick question. Yes.
okay, Mr. Tan, you're right. The Penang scenario is much easier, probably because marine clay and granite. Okay.
Okay. Yeah.
That's
any
the
other question? Any other question from the floor? From
That's
the
the
audience?
geology. But I think I let the floor question first.
Yeah.
Before I continue.
Right. I see Mr. Fateh Chan, our very senior guy here. Are you there, Fateh? Fateh Chan? Not there. Okay. Anybody else? Our audience, as usual, is very quiet. Okay, Robin, continue, Robin.
I saw these questions on the chat box.
Oh, okay. Can you read it then, Engineer Khoo?
The question is from Hafizi. Is there any geophysical survey done at the site? So short answer is apparently no. No
Okay.
geophysical survey undertaken.
Okay. Answer is no lah. Okay. All right. Next question. We still have about 10 minutes. Sorry, I had to cut short the speaker. We overrun the time. Yeah. Anybody? Otherwise, Robin, continue then, Robin.
Okay. Since no takers.
Yeah, we are very quiet, audience.
Okay. What I call this, yeah. Thank you, Mr. Hafizi, asking about the geophysical survey. I think geophysical survey not necessarily lah. We have a direct method or borehole. Borehole is very direct already, so there's no need for a geophysical survey. Yes. So, Engineer Khoo, just now when you mentioned about this, the problem with the large ground depression, localized subsidence, because of the boreholes, even though the borehole size 4 inches, is it in diameter? You say?
Yes.
And even doing that boring, and that caused subsidence. I was thinking about when you say the subsidence, localized subsidence. I was thinking about liquefaction of the alluvium. Liquefaction of the alluvium because of the vibration due to this drilling machine. And and then this mining issue. So I was thinking about, mining tailing, because the lithology is such that the sediment is chaotic. Is as you in the slide you show, it's gravelly, sandy, silty, clayey. So it is what you call this mining activity. But then expert B, C say the SPT value high, so it's not possible to have this mining tailing, because mining tailing is slime. So we expect n equals to 0. So in the end, you conclude is due to fluctuation of this fluctuation of the groundwater in the alluvium. So so is that the problem? Is the fluctuation of this groundwater, and it's also incomplete settlement of the sediment. So the sediment is still compacting. Is that reason? Because incomplete compaction of the sediment over the limestone that caused the subsidence? It seems to be. It seems to be.
Well, thank you, Mr. Robin, for the questions. Right. I think it's interesting to look at this. Right, can you hear me? Can you see the slide? So we can see they're almost a similar kind of patterns of the ground depressions. It's actually extending outwards from the epicenters. Right. In this case, when the grouting holes is carried out, and even at the first incidence, the epicenter is at a distant away, then it extends outwards radially in a circular shapes. Then it starts to sink progressively with time, taking time. So, and we know that the slime zone is at depths about, let's say, 80 meters, 90 meters below ground. And the first incident occurred when the borehole actually they're extracting the rods, right? So one of the possible scenario, personally, I believe is due to the groundwaters, as Mr. Robin highlighted, but I can't believe it's due to the liquefaction of the sandy materials, because it's quite clayey at certain depths. And it could be, you can look at the shape, it's just like cone or depression, something related to effect generated by a pumping well. When you pump the groundwaters, then the water start to going towards the well, then create a ground settlement. This could be quite a similar case. It's very good case study. And furthermore, we understand that for the first incident where the contractor actually extracting the rods, it in some way created some suctions. So it created some suction to bring up the groundwaters, like pumping, then it caused water start to saturate at the site and depress and lower down in this case. That would, I think, one of the possible scenarios.
So in conclusion, it's due to this groundwater withdrawal.
Yeah, it's quite similar to that kind of effect.
Okay, thank you, Engineer Khoo. But this one, I really need to know. I really need to know. Besides this, what I call this engineering, engineering geology, the geological aspect. This is the first time anybody in my webinar. I think I've attended more than 30 webinars already. First time mentioned about Hotterdon schist. So maybe Engineer Khoo, could you show me the location of the Hotterdon schist? Is it possible?
Apparently not within the confine of these maps. Where we encounter Hotterdon schist is line 2 located near to Kepong Central. Kepong Central, okay. There is what the Jalan Dagang, is it? Where the foundations for the viaducts and crowding these materials.
All right.
I think it's also indicated the geological map, but just not within my snapshot here.
Yeah, Robin, there's a question on chat. Engineer Khoo, can you read the question? On chat, Rob.
So this is again from Hafizi. Yeah. Okay, is there this answer? Oh, sorry.
Can you read the question?
Chris, yes. Can I know if comparing site area with old maps is a common practice for underground work planning, or was it adopted due to the issue faced at the project? Yeah, this is a good practice. Perhaps in our KV MRT projects, we have this requirement to carry out historical land use survey. So, which includes from this engineering and geology study of the area photograph or historical photograph, what were the lands being used before? Because like in this case, we know that other than the mine filling issue, however, we also know that there were certain period that the ground is actually the area actually there are buildings located there. So with the building, there is possibility of the foundation leftover foundations. It may cause some problem when we doing the excavations. So perhaps there are some RC power encounter during the box excavations.
Yeah, I think it's a good practice. It's a part of the death study before you do actual construction. Yeah, check the history. Okay,
Yes.
I see a familiar name in the audience. Ilani, are you still there? Oh, no response. Ilani, are you there still? Okay, I think some of them. Okay, never mind.
These are the photo showing the power encounter during excavations.
Yeah.
I think there's another question on chat. If geophysical survey are not needed, then what kind of survey are done? So for Mariam, I think he or she is referring to the site investigation, right? So in this case, of course, the typical borehole explorations. Then of course, because of all the issue, we have additional borehole with the continuous samplings, all that.
Okay, I think it's about time. Maybe one last question. One last question. Sorry, somebody.
Mr. Tan?
Yes.
Yes, yes. Thank you, Engineer Khoo, for this. Most delightful, most informative. What do you call this? Technical talk. So thank you very much. And yeah, to answer Mr. Muklis, Mariam, answer a question just now. Yeah, of course, we need to do what you call this. The historical work on the ground that we were looking for, whether the area was a mining area or not mining area, whether it's mine tailing or not mine tailing. So we do have to do a historical background check. And Mariam, geological survey, we do geological survey as a preliminary investigation. In this case, we have no need because we already have bore log and we already do the SPT test. There's really no need for a geological survey. So Engineer Khoo, there's one more
questions in the chat.
One more check.
Yeah, I know that you are pretty interested about geophysical survey, although we didn't do any geophysical survey at your SKL site, but the second side that I want to show, actually we did microgravity methods. It's quite useful also in the shale limestone. There are also surprises encountered. So yeah, for other side we did no only microgravity, we are using normal MSW, RI, resistant, all that to supplement the borehole investigations.
Okay, I think time is up, so we close the session. But before we do that, can all of you